This is the continuation of our talk regarding data structures and data management. In previous lecture we talked about vector data. In this lecture we're going to be talking about raster data. Table of contents of my talk in this lecture. We're going to look at, as I said before, raster data. How do we create raster data? But prior to that, we'll be looking at some of the characteristics of raster data. Once we identify the common characteristics of raster data, then we're going to look at how do we create raster data, how do we store raster data, and there are a number of methods. And then lastly, in this lecture, we'll compare which data structure is the preferred structure. We're going to compare raster versus vector. Some characteristics about the raster structure. A raster structure represents data as a regular grid or a series of square cells. And a combination of these square cells or pixels would constitute the entire grid or the view of the phenomena that you are mapping. The location of each cell or pixel, which is another name for picture element, is defined by its row and column number. So each cell would have a unique row and column number on that particular image. Values can be assigned to each pixel. For example, a pixel can be representing water bodies, other pixels can be representing vegetation, or other pixels representing urban areas, etc. This is two examples of your grid, where we're looking at two types of grid, continuous grid and categorical grid. In a continuous grid, you can see there's a transitional boundary, meaning that there's no abrupt change in the particular phenomena being showed. This is a more realistic representation of what occurs in the real world, because in the real world we don't have sudden changes in boundaries. We have a transitional change. For example, if I want to represent temperature changes, there would be a gradual change of values in terms of temperature values from one, let's say for example, from a warm area to a cool area. All right. Now, in this example, you're seeing each cell is stored with a unique value, and it's representing bathymetric depth. Now, the other type of grid, again, each pixel has a number, but in this grid, categorical grid, the data is classified. All right. So what we are saying here is that it will assign, for example, if the pixel values range from 0 to 100, we'll assign all of them a value of 1. Between 100 and 200, we'll assign a value of 2. Between 200 and 300, we assign a value of 3, etc. Now, once you start creating these categories of classification of pixels, you would have to add a attribute table representing what each one of these new cell values represent, and the system will actually count how many cells for each cell value, and then you would add in one of the columns what type of let's say categories in terms of land use, in terms of the values that you have chosen to represent that data. You see here another example of some of the characteristics of what the raster structure covers. It covers the entire area into a regular grid of cells in a specific sequence, and it's usually row by row. So row then the following row, and the XY, the 0, 0 usually is at the top left hand corner. Each cell contains a single value, so each one of these cells is going to have a unique value. That is if you're using the raw data. That is if we don't classify the data. Each cell contains a single value, and it's space filling. In a raster structure, every cell would have a data value associated with it, even though if it might not be part of the phenomena. If it's not part of the phenomena for that layer, it's going to be assigned a value of 0, 0, 0, representing that particular phenomena not existent there. It tells what occurs everywhere. So every cell is going to tell me, it's going to give me some sort of information. Raster database can consist of many layers. We can have many raster layers overlaid onto each other once they're properly georeferenced and they use the same coordinate system. We can use them in our application. Example, we have soil type, elevation, land use, land cover, and many others. I'll give you an example in the next slide that gives you an idea of how to represent the raster data structure. But in this diagram here, you're seeing the cell, each cell has a specific height and width, and the height and width is the same. If I choose a 2 by 2 grid cell or pixel value, it's going to be 2 whatever units, so 2 meters by 2 meters is the resolution. This is an example of raster data being created from your vector data. So this is my vector data that was captured from the real world. I captured topography by way of contour lines. I've captured the soil types by digitizing the polygon areas, and I have captured the forest types by digitizing in vector the polygons representing the forest types. Then I would use the GIS software to rasterize this vector data into raster. So you do a rasterization process. You get the forest types in a raster format. You get soil types after rasterization. You get the soils as a raster data. And similarly, your topography, you have the topography as your raster data. I can overlay all of these 3 of them and then build a query and select specific cells that satisfy my criteria. And my final result is shown there. So another example of raster data, multiple layers being used. We have watersheds being shown up as raster data, slope information, raster data, it's a black and white. Soils, raster data, land use is a raster data, animal loading areas, raster data. And what they did here is use all of these layers, did analysis, and came up with a result indicating agricultural pollution potential, where based upon my entire study area, let's say this is my property boundary of the entire farming area that I'm doing agriculture, I want to identify the potential pollution, agriculture pollution, using all of these data sets. Very useful application. Now, how do we create a raster? Raster structure can be created using one of the old traditional methods before the time of scanners and satellite imagery. You can create it using a word processor or database by typing in these values. You can either type it in one value per cell per line, or it can be continuous, or you could do a handwritten, which I'll explain in the next slide, the different types. So one method of creating raster is by using a word processor. It's not being used nowadays because the technology has greatly advanced, but it's a method. Another method is digitizing existing maps in the vector formats and then converting them into raster formats. So by capturing the data using a digitizing table in the vector using vector structure, and then I would rasterize it, and I can get raster data. Scanning the hard copy maps using a scanner, we are directly getting raster structure being created using scanners. Or we can get data readily from remote sensing satellites. We can go to these on these websites where they are ground receiving stations that provide georeference satellite imagery that are all raster structure. This is an example of the old traditional method of capturing or creating raster data using a processor, word processor. You could either type in the values row by row. So if this is my image, I want to be able to create the value for this cell is 1, 1, 1, 2, 2. Then hand return, go back, 1, 1, 1, etc. Or I can enter each value on an individual line. So the first cell is going to have a value of 1, the second cell of 1, third cell 1, and each value is going to be on a new line. Or I can enter them continuously, and when the system reaches the end of that particular view in the limitation in the word processor, it will continue on the next line. So 3 methods, and as I said before, this is very tedious, time consuming, and also error prone, but it's a method of capturing or creating raster data. We can also create raster data using, as I said before, digitize using a digitizing table vector features, and then we would use the GIS software with that has the rasterization process. It will take this vector data as input into the process. It'll go through and prepare, do the processing, and then finally it's going to create this same vector in the raster format. And what you can see here is that nothing, where there is nothing that was captured, a value is still being stored for it. So a value of 0 indicates no water feature, and 1 represents water body, 2 represents the river. In this slide, I try to give you some information regarding cell values in a raster structure. Cell values depend both upon reality being coded. For example, if you're using raster data and you're assigning values for the pixels, it is highly recommended that you use pixel values that mimic certain characteristic of the phenomena that is being mapped. For example, trees may be coded as a numerical value or alphabetical value, but your GIS software can choose using the GIS software. You can choose either numeric or character. Different systems allow different classes of values. So when you're planning to use a GIS software, make sure, and you want to use raster structure, make sure it has the flexibility that you want it to have in order to assign values to each pixel based upon your intended analysis. So different systems can have here, for example, pixel values being whole numbers or integers. You can also use real numbers with decimal values. You can use character values or alphabetic values. What you're seeing here in this little graphic is we're using real numbers with decimal values. So this is an ideal example of probably a DEM, a digital elevation model. And this is another graphic of using whole numbers. And what you're seeing here is that values assign a specific color to the cell. And it also means that each value has a specific attribute information. Integer values often act act as code numbers which point to names in an associate table. This is what I'm talking about, the associate table. It might be a data dictionary or some sort of an attribute table that is connected to your raster data. For example, 1 can represent roads, 2 can represent building, and etc. This is another example of raster data values. Here you're seeing numerical values representing different soil classes. So 1 is going to be probably clay, 2 sandy soil, 3 gravel, etc. Here, and the other example here is where they use decimal values representing each pixels represent a height above mean sea level. So this raster data that shows elevation, for example. The last one here is using characters or non-numeric values. I want to be able to use this to represent vegetation classes. Alright, so they use A, B, and C. And together with this is going to have an associated attribute table indicating what does A represent, what does B and C, etc. Now, let's move on to look at how do we store a raster structure. And there are 3 methods used to store raster structures. 1, full raster encoding. 2, run length encoding. 3, quad tree representation. A little description about what is entailed in raster encoding, some of the characteristics. Well, each cell having its particular code is stored individually. So the system stores each cell individually. Now, because of that, is actually if each cell is stored individually, then it will be very demanding in terms of storage space of raster data. Alright, so there's a problem of storage space, not enough storage space, especially if your data set is large and you have multiple layers. Also, processing speed is reduced because in order for the system to do processing of data, it has to recall each individual cell and be able to put them together to form their sample area and then do the analysis. And also there's redundancy in your database. Now, as I said in previous lectures, redundancy or repetition of in databases is looked upon as being bad. You want to be able to reduce or minimize redundancy, and full raster encoding has a lot of redundancy. Now, this is a very important diagram. I would strongly urge you to pay particular attention to this diagram because it explains how raster data structures are compressed. Under the standard run length raster encoding, there are a number of methods. You have the full raster encoding, which I discussed in previous slide. We have run length encoding and value point encoding. Now, in the full raster encoding, as you said before, each cell in the entire data set are stored individually. So it will store this A, all of them all together. So all together, to store this particular data set, which is a representation of this map here, all right, it will store 100 values. Now, the other compression method to store your raster structure is called your run length encoding, and in this method, it stores this whole image. It would have stored 100 values here in the full raster encoding. In the run length encoding, 54 values are stored. And how it works is that it will identify all of the values for each run. So this is one run, this is another run, and then another run, etc. And whenever there's a change in the value, it's going to have a short run here, but starting with B, and it'll go to the end of it. So how it works is that value A is put under the value column in the run length encoding, and the length is that counts the number of A's in that particular run, and it will put that length as a coordinate under the length column, and it will identify which row. This is row 0 and it's row 0. So for this entire row, this run, it's actually storing 3 values, A, 10, and 0. For the second row, you have value A, you have 10 of them again, and it's row 1. The second row, it starts with A, and there are 4 of them, and it's in row 2. And also on row 2 we have B, which is B here, and you count the number of B's, and there are 6 of them, and it's in row 2. So all of this has been stored in a compressed version on the 3 column: value, length, and row. Collectively, it stores for that same image 54 values. Now, another method of further compression of the original image is what we call value point encoding. Now, value point encoding, you start for the value point encoding, start counting from 0. So you start saying this is 0, 1, 2, 3, 4, etc. So make sure that you start counting this A as starting from 0, because that's your 0, 0. All right. So what in the value point encoding method, there are 2 columns: value and point. The first value is A, and you start counting 0, 1, 2, 3, 4, 5, 6, and then until it reaches this location here, which is point number 23. So it will store all of these A's by these 2 values: value A, and it counts until 23. And then value B, which is here, and it goes on until point 29. So from here to there is 29. This is the where it stops in the image, and it will do the entire image by just putting the value at the point where it's located on the image. Now it's not adding up the number of cells; it's the point location on the image. Compare this compression method. It only stores for this entire image, original image, 32 values, compared to the original would have been 100 values. Value point is very, very useful. All right, so what you need to know in value point, make sure that you start counting from 0, 1, 2. So the first pixel is going to be number 0. Also, you need to note here in the value length encoding, your first row is numbered 0. So note that also. This is some notes about the other method we talked about, the run length encoding. Adjacent cells along a row that have the same value are treated as a group called a run. The value is stored once together with the information about the size and the location of the run. So it's very useful in terms of compressing that raster structure into a smaller, manageable entity where it can be stored, taking up very little space on the hard drive of the computer. There are 2 types of run length encoding, which the previous slide showed you in terms of diagram. The standard run length encoding, the value of the attribute and the number of the cells in the run and the row number are recorded. So 3 columns of information are recorded. But the value point, we have 2 columns. As I said before, the point column and the value column. The point column indicates the position at the end of each run is stored on the point column, and what is the value that you are actually counting in terms of the cell value. Remember, as I said before, start counting from the first entry with the number 0. Do not start with the number 1. So always start with number 0. Which is the preferred method? More compression is, of course, your value point encoding. method of compressing your raster structure is what we call quad tree representation, and this is popular, becoming very popular in most of the GIS software. And what it does is actually making use of usually man-made features that we want to capture and store in the raster structure. And this is an example of what I'm talking about here. This is a feature we want to capture in the raster format, raster structure, sorry. What it does, if you want to store it as a quad tree representation, the entire study area is divided up into quarters. Alright? And if you look at the quad tree representation, this is the quarter that we talked about. And then wherever there's further subdivisions, alright, so there are more. If I can divide this up into also another quarter section, there's nothing here, nothing here. Alright, there's nothing here in this big cell. But there are more information here, so I'll divide this cell into quarters. Alright, there is some information here, there is some information here, there is information here. There are more information, so I'll divide up into quarters again. There is none here, no information. There is some information here, and we'll have to code that in. There is more here, so I'll divide up in further quarters, and likewise here, further quarters. Up on this area here, which is on this area in the original image, I'll have to have further subdivisions. And likewise in certain areas. Same sort of concepts. It's actually divided up in the area of the map into a set of quarters, quarter sections. Okay? It provides a more compact raster representation by using a variable size grid cell. So as you will have seen in the previous slide in the diagram, where the big area is actually a big pixel, and that entire pixel will be stored because there is no further finer resolution that needs to be captured. Finer detail areas will require the grid to be further subdivided. That is where I'm talking about divided up into quarter sections. Finer resolution or smaller cells is used for areas of high spatial variability, meaning that there are more detailed information that we need to capture and represent. And I give you another example in the following slide in terms of a practical example. Here you see it's man-made subdivision in terms of a land use map where we have industrial, rural, multi-unit residential, we have residential detached, commercial, and some other areas here in terms of A and B. I want to be able to use the quad tree representation to represent this map. A is being a community service, B is recreation. So I'm going to be able to use this. So again, the concept divided up into quarters, the entire study area, this is a quarter. So we have the industrial area being represented by this 0 and a 1. And we have the rural areas being shown up as, this rural areas as number 3. And there are more detail here, so obviously I need to divide up into quarters. Okay. And this is going to be my number 2 section. And I'm numbering that in a clockwise direction. So this is 2, 0, 2, 1. Actually, it's 2, 0, 2, 1, 2, 2, 2, 3. Okay. And then what we have here is that 22 and 23 is part of the residential multi-unit. 20 is residential detached. And we have further subdivision here. So divide up into quarters. Then you have 2, 1. 210, 2111, 2112, 2113, and then I can represent these using these ID numbers. How does the table, what does the table look like? Well, this is the table here, table of attributes. We have the different quad tree levels, level 1, 2, and 3, and we assign these numbers to the different land use types. So 0 was assigned industrial, which is industrial. 1 was assigned industrial. 2 was assigned there are further subdivisions here, so it's residential detached. So 2 is residential. 2, 0, which is this area here, is residential detached. 2.1, which is here, is services. And under services, we have a third level. Quad 3 is 2.10, 2.111, 2.112, 2.1.3, which is all of these here. And that's where I could put in the attributes for each one of these here, land use types. 2.2, 22 is your residential multi-unit. 2.3, residential multi-unit. And 3, level ID number 3, is your rural attribute information. So very useful in terms of how we store the raster data, raster structure in the quadro representation. And what is very important to note is that the cells are actually variable. Larger the cell means that there is not much change in terms of the details of that particular phenomena being captured. So a big scale cell is stored there as opposed to smaller cells being stored here where there are more detailed information. This is another similar approach in terms of how do we use quadro representation, and they're using again numbers, and what you can see here is that they are larger cells, so obviously these are larger clumps of information that require no further subdivision. These here require further subdivision, and they assign different levels of the quadro representation. This does not, etc. Major disadvantage in your quad tree representation is the time it takes to create and modify the quad tree. It takes a lot of time to do this. Alright, once it's done the first time, updating is not going to be, it'll also take some time, but once it's done, it works very efficient. It requires more processing time to generate the quad tree with these indexes. I want to be able to link whichever attribute information is linked to the particular pixels or collection of pixels. If the data is fairly homogeneous, meaning there is not much changes, or if there's not much details that I want to show, then quad trees provide an efficient storage. Fewer the classes of these cells, larger the clumps, greater the degree of compression. So that's what I want to get. If my phenomena does not have much of detailed information, I would use a quad tree structure. Best utilized when the need for updating is not frequent. So yes, you're going to have to update it whenever there are some changes, but if there in a system, in a raster structure that doesn't require much updating, this is the preferred method. Alright, let's move ahead just to compare raster and vector. Now, the question is, which one is the preferred method? Is it raster or is it vector? The answer to that is neither. It all depends upon what is the intended application, and a lot of the GIS application is actually focused towards using the raster and also the vector structures. Now, some advantages of a raster model. It is simple. It is a simple data structure, very easy to understand. Overlay operations are easily and efficiently implemented, easily to do overlays. High spatial variability is efficiently represented in the raster format. I can show graduation in terms of transitional changes along boundaries of particular phenomena rather than the abrupt changes in your vector structure. The raster format is more or less required for efficient manipulation and enhancement of digital images. Digital images, the only way you can work with them is in the raster format. So, very good and useful method of representing data using the raster structure. Disadvantage, the raster data structure is less compact. Data compression techniques are very important. And sometimes when you compress the data, it might affect your analysis. Okay, so that's what they're saying here. it can often overcome this problem. There are different techniques to do these things, to do the compressions. Topological relationships are more difficult to represent in your raster. We previously talked in this lecture about being able to build the intelligence in your GIS. Well, in your raster data, it's difficult to do the topological relationship definitions. The output of your raster data is usually, depending upon the pixel resolution, can be very gritty if you're using large pixel sizes. If it's small pixel sizes, the final printout can be very good. But if it's large pixels, it can be less aesthetically pleasing, especially where the boundaries of particular phenomena that has been shown up, that is as part of your output in your GIS application. Let's look at some of the advantages of your vector structure. Advantages: it provides a more compact data structure than your raster model. Remember, in your vector model, you typically store coordinates of points, okay, to represent point, line, and polygons. It provides efficient encoding of topology. It's very efficient in building that intelligence into your GIS database, being able to tell the from node, to node, the left polygon, the right polygon, which we talked about earlier on in this lecture. The vector model is better suited to support graphics that closely approximate the hand-drawn maps. So vector model, it's like taking a pen to paper and drawing a map. And that's what they're saying in this advantage. It is what we would typically do if we draw a map by hand. The disadvantage is more complex data structure than a simple raster because of the topology definitions on how we build that intelligent database. Overlay operations are more difficult to implement. But they're saying, yes, we can do some overlay analysis in vector, but remember, in your vector structure, the data is not space filling. All right. So if I want to get an area that is defined within a particular polygon, it's going to be you're going to have to do much more steps in order to get that area that I'm interested in getting, because wherever you're selecting a particular polygon, the entire polygon is being selected. The representation of high spatial variability is inefficient in terms of being able to show boundaries that are in transition. All right, changes in temperature from hot to cold. There's not a sudden change in temperature as the vector structure would show, but a transitional change. Manipulation and enhancement of digital image cannot be effectively done in the vector domain. So I cannot say, well, I have a GIS software that does vector. I want to be able to process raster data. I want to process imagery. That's impossible. All right, this map here shows examples of a data set available from Pakistan. This is available, I got it online. This is vector data with a number of layers overlaid onto each other, and we have a very good map displaying road network and different polygons and the neighboring countries, things like that. But also, we can do the same thing in the raster environment. Here you see a map of satellite imageries from Landsat 7 imagery, together with some spot satellite information. All of these it looks similar in terms of the extent, but the actual data being shown up here is representing different phenomena. So very useful. We have vector, and here we have raster. All right, we can overlay actually this vector data with the raster and have one map combined together. This is another graphic of how we can integrate vector data of a study area. Once it utilizes the same coordinate system and projection system, I can overlay my vector structure with my raster data and put them all together. We are representing a certain phenomena from the real world. So here we have land use, elevation. Land use and elevation is raster structure. Parcels, streets, and customers, they are all vector structure. put them together, we come up with different applications. Alright, this concludes our talk about data structures and data management. I strongly advise you to download the PowerPoint notes page. Go over the material, make sure you understand it. Go over the PowerPoint show, and if you want to hear over the audio, run it over. Make sure that you understand the concepts, and we'll continue in the next lecture.